Numericals on bonding in solids. The first numerical. Find ionic cohesive energy for cesium chloride. Madelung constant for which is 1.763. Separation between ions is 3.56 angstrom. N is given 10.5. Ionization energy of cesium is 3.89 and electron affinity of chlorine is 3.61. So let's write what are the given quantities. Alpha is given, Madelung constant, which is 1.763. R naught is given, the separation between ions is 3.56 angstrom. Then a constant N is given, 10.5. Ionization energy of cesium is given 3.89 electron volt and electron affinity of chlorine is 3.61 electron volt. So these are the quantities. Let's first find potential energy per ion pair. Formula for it is V equals to minus alpha E square upon 4 pi epsilon naught R naught into bracket 1 minus 1 upon N. From this formula we can find potential energy per ion pair. Let us substitute the values. This minus alpha is given 1.763 into E square. E is the charge on the electron, which is 1.602 into 10 to power minus 90 coulomb. You must know the values of E. It would not be given. Divided by 4 pi is 3.14. Epsilon naught is a permittivity of free space. You must know its value, 8.85 into 10 raised to minus 12 into R naught. R naught is 3.56 angstrom. That is 3.56 into 10 raised to minus 10 meter. We have to consider this in SI units. Then into bracket 1 minus 1 upon 10.5. So this comes around, numerator is 4.513 into 10 raised to minus 38. This is E square over here. So E square into the value of alpha is minus 4.513 into 10 raised to minus 38 divided by, let us multiply these quantities, 4 into 3.14 into 8.85 into 3.56, which is equals to 395.72 into 10 to power minus 22 into, this is equals to 0.905, that is 10.5 minus 1, that is 9.5 divided by 10.5 is 0.905. After multiplying this, what we get is 0.01032 into 10 to power minus 16 joules. Or let's write like this, 10.35 into 10 to power minus 90 joules. Let's convert this into electron volt, that is minus of 10.35 into 10 to power minus 19 divided by 1.602 into 10 raised to minus 19, and this is in electron volt, which is equals to minus of 6.45 electron volt. So potential energy per ion pair is 6.45 electron volt. What we have to find in this case is ionic cohesive energy of cesium chloride. So for that, we know that for the formation of ions, for the ion formation, ionization energy of cesium is 3.89, and electron affinity of chlorine is given 3.61. It means that if you supply energy to the cesium equals to 3.89 electron volt, it gives us cesium ion plus electron, and chlorine ion plus electron is that gives us chlorine ion plus 3.61 electron volt. So this energy is released and this we are supplying. So net energy required for ion formation that is one cesium and one chlorine ion is equals to ionization energy minus electron affinity that is 3.89 minus 3.61 equals to 0.28 electron volt. So this energy we have to supply to get one cesium ion and one chlorine ion. The cohesive energy, what we have to find is cohesive energy. Cohesive energy is potential energy per ion pair minus net energy required for ion formations. That is minus of 6.46. This is 6.45 over here. So 6.45 minus 0.28, and that is equals to minus of 6.18 electron volt. So this is the cohesive energy of cesium chloride. Let's go to the next sum. Numerical number 2. The energy of two particles in the field of each other at a separation r is given by, what is given is phi, equals to minus alpha upon r plus beta upon r raised to 8, where alpha and beta are constant. At what separation they will form stable compound. So let's solve this. For stable compound, interatomic distance r should be equals to r naught. R naught is bond length. That is, the two atoms are at equilibrium. So at equilibrium distance, resultant force is zero. That is minus of d phi by dr at r equals to r naught is equals to 0. We have the equation here. This one is given here. Phi equals to minus of alpha upon r plus beta upon r raised to 8. So let's take this minus of d phi by dr at r equals to r naught. Phi is this. Let us take the derivative of this with respect to r, and it is minus alpha upon r naught square. R equals to r naught plus 8 beta upon r raised to 9, and this is equals to 0. Let's simplify this further. Alpha upon r naught square is equals to 8 beta upon, this is r naught raised to 9, or r naught raised to 9 divided by r naught square is equals to 8 beta upon alpha, and that is equals to r naught raised to 7, that is equals to 8 beta upon alpha, or r naught is equals to 8 beta upon alpha raised to 1 by 7. So we got this distance r naught. At this, they are stable. The stable compound is formed. Then sum number 3. The potential energy function is expressed as minus alpha upon r raised to 6 plus beta upon r raised to 12, where alpha and beta are constant. Show that the intermolecular separation R naught, for which the potential energy is minimum, is given by 2 beta by alpha raised to 1 by 6, and the minimum potential energy phi naught is equals to minus of alpha square upon 4 beta. So intermolecular separation R naught, at that the potential energy is minimum. So we have to find this intermolecular separation R naught, for which we know the phi is given. Phi is equals to minus alpha upon r raised to 6 plus beta upon r raised to 12. So we're going to take minus of d phi by dr at r equals to r naught, which is equals to minus of 6 alpha upon r naught raised to 7 plus 12 beta upon r naught raised to 12, 13, and that is equals to 0. Simplify it. 6 alpha upon r naught raised to 7 is equals to 12 beta upon r naught raised to 13. or R naught raised to 30 divided by R naught raised to 7 is equals to 12 beta by 6 alpha. So further simplify it, we get R naught raised to 6 is equals to 2 beta upon alpha, or R naught is equals to 2 beta upon alpha raised to 1 by 6. This is the first part. Then it is what is asked, the minimum potential energy is phi naught equals to minus alpha square by 4 beta. This we have to prove. So we have the potential energy, second part. Potential energy is given, that is phi is equals to this equation, minus alpha upon r raised to 6 plus beta upon r raised to 12. Therefore, the potential energy at r equals to r naught. We denote it by phi naught. So phi naught is equals to minus alpha upon r naught raised to 6 plus beta upon r naught raised to 12. In this, we are going to substitute the value of r naught over here. Therefore, phi naught is equals to minus alpha upon this r naught is 2 beta by alpha raised to 1 by 6. So this is 2 beta upon alpha raised to 6 into 1 by 6. So this is 1 by 6 and this is raised to 6 plus beta upon r naught is 2 beta upon alpha raised to 1 by 6 into 12. So this is equals to minus alpha. This 6 cancels with this 6. What we get is 2 beta upon alpha plus beta, this into 2. So what we get is 4 beta upon alpha square. Let us further simplify this by taking alpha up. So minus alpha square upon 2 beta plus beta upon, this is beta square. So beta alpha square upon 4 beta square. That is nothing but minus alpha square upon 2 beta plus alpha square upon 4 beta. Simplify this, minus 2 alpha square plus alpha square upon 4 beta. 4 beta is LCM and that is equals to minus alpha square upon 4 beta. This is minimum potential energy. We have proved it. Then the fourth sum is compute the net potential energy of system sodium and chlorine ion pair. The equilibrium distance between the ion pair is 0.28 nanometer. So what is given here is R naught 0.28 nanometer, which is 0.28 into 10 to power minus 9 meter. We know the relations for potential energy, which is V equals to minus of E square upon 4 pi epsilon 0 R0. Let us substitute the values. So minus of 1.602 into 10 to power minus 19 and square of this divided by this 4 into pi 3.14 into epsilon naught 8.85 into 8.85 into 10 to power minus 12 into R naught. R naught is 0.28 into 10 to power minus 9 meter. And this is in joules. We want this in electron volt. So minus of 1.602 into 10 to power minus 19 square divided by this multiplication 4 into 3.14 into 8.85 into 0.28 is 31.124, and the power here is minus 12, here is minus 9, that is 10 to power minus 21 into 1.602 into 10 raised to minus 19. So this is in electron volt. This was in joules. So in this, one cancels with this, and minus of then 1.602 into 10 raised to minus 19 divided by 31.124 into 10 to power minus 21, and this is equals to 5.15 electron volt. So potential energy is 5.1 electron volt. Next, sum number 5. Calculate the cohesive energy of NaCl from given data. The equilibrium separation of sodium and chlorine ion is 0.28 1 nanometer. Mu is given 1.748 into 10 raised to minus 28 joules meter. N is 1, M is 9. Let's write given quantities. Given R naught is given 0.281 nanometer, that is 0.281 into 10 raised to minus 9 meter. Mu is equals to 1.748 into 10 raised to minus 28 joules meter. N equals to 1 and M is equals to 9. What we have to find is the cohesive energy of NaCl from given data. So this equations we have to use potential energy phi naught is equals to minus of mu upon R raised to n into bracket 1 minus n upon m. These values are given. So let us simplify this. Minus 1.748 into 10 raised to minus 28 mu divided by R naught. R naught is 0.281 into 10 to power minus 9 raised to n. N is 1. So this is raised to 1. Then into bracket 1 minus 1 upon 9. So this is minus of 5.529, not minus, minus of 6.22 into 10 raised to minus 19 into this 9 minus 1, that is 8 by 9, and this comes around 0.529 into 10 raised to minus 19 joules. Convert it in electron volt, divided by 1.602 into 10 raised to minus 19. This is in electron volt. and that is equals to minus of 3.45 electron volt. The next sum, the potential energy of a diatomic molecule is given in terms of the interatomic distance r by expression phi equals to lambda upon r raised to 10 minus mu upon r raised to 2. Calculate equilibrium spacing between atoms and dissociation energy. Given mu equals to 1.44 into 10 raised to minus 19 joules meter square and lambda is 2.19 into 10 raised to minus of 115 joules meter raised to 10. So we have the expression over here. This phi is equals to lambda upon r raised to 10 minus mu upon r raised to 2. So from this equation, here n is given, which is 2, and m is equals to 10. Let us So we have to find the potential force. The potential energy, see, the of diatom molecule is given. Calculate equilibrium spacing. We have to find the equilibrium spacing between atoms. Equilibrium spacing between atoms, that is, we have to find R naught, and this phi is given. So what we have to find is the resultant force is 0 when R equals to R naught, which is 10 lambda upon r naught raised to 11 minus mu upon r naught raised to 3. 2 mu upon r naught raised to 3, and this is equals to 0. Let's simplify this. R naught raised to 11 upon r naught raised to 3 is equals to 10 lambda upon 2 mu, that is 5 lambda upon mu. So this r naught raised to 8 is equals to 5 lambda upon mu, which is equals to lambda is given in this case 2.19 into 10 to power minus 115 into 5 lambda divided by mu. Mu is 1.44 into 10 to power minus 39. So r naught raised to 8 is equals to 7.604 into 10 to power minus 76, and hence R naught is equals to 0.408 nanometer. So this is the equilibrium distance between the atoms. Now at this equilibrium distance there would be the minimum potential energy, and that minimum potential energy is equals to the energy of dissociation. So minimum potential energy, at minimum potential energy is nothing but energy of dissociation. The formula for that is, the phi naught is the energy of dissociation. We have to find energy of dissociation. So phi naught is equal to minus of mu upon r naught raised to n into 1 minus n upon m. Let us substitute the values here, which is minus of 1.44 into 10 to power minus 39 upon 0.408 into 10 raised to minus 9 square, because n equals to 2 in this case. From this equation, n equals to 2 and m is 10. So r naught raised to n, that is square of this, into bracket 1 minus n is 2 and m is 10. Let us simplify this further. minus of 8.65 into 10 raised to minus 21 into 8 by 10. This is equals to 8 by 10. Hence, minus 6.92 into 10 raised to minus 21 joules. Let's convert this in electron volts. So, minus of 6.92 into 10 raised to minus 21 divided by 1.602 into 10 to power minus 19 coulomb, and this is equals to minus of 4.32 into 10 raised to minus 2 electron volt. That is the answer.